Welcome to the lecture on IoT in safety critical context, which is part of the Safety Informed Security lecture series for Cyborg. This lecture brings everything we covered before together by looking at IoT systems that do not only process data but also observe, influence, or control the physical world. And the central point is that safety critical IoT changes the meaning of failure. In an ordinary digital system, a failure may mean loss of data, loss of service, or unauthorized access. In a safety-critical IoT system, the same type of cyber failures may affect people, physical assets, industrial processes, vehicles, medical treatment, or essential services. So the purpose of this lecture is not simply to describe IoT applications. The purpose is to understand why IoT becomes safety critical, how failures propagate through connected systems, what operation challenges arise, and how real incidents show the connection between cyber compromise and physical consequence. The lecture map to the following to the two cyber knowledge areas. The first is the cyber physical system security. This is the main area for this lecture because safety-critical IoT systems are cyber-physical systems. They combine sensing, computation, communication control, and physical processes. The security cannot be analyzed only in terms of information protection. It must also be analyzed in terms of how attacks affect physical behavior. The second is the risk management and governance. Simply because safety-critical IoT systems require decisions about acceptable risk, operational assurance, responsibility, monitoring, and mitigation. These systems are deployed in environments where failures may affect people and public services, so risk management is not optional. The lecture also partly connects to network security and physical layer telecommunication security, simply because they are relevant for many IoT systems which rely on wireless networks, gateway, low power protocols, communication links, and they may be disrupted, delayed, intercepted, or manipulated. So what we're going to cover, the lecture is organized into 5 main parts. We're going to define the characteristics of safety IoT systems, safety critical IoT systems. We'll explain what make them different, and so on. Second, we look at failure propagation in IoT systems. This is the idea that a fault or a cyber incident may begin in one component but spreads through communication, processing, actuation, and finally the physical process. And third, we examine operational challenges, including real-time constraints, continuous operation, complexity, human factors, and trade-off between safety, security, and performance. And fourth, we look at the safety-critical domain examples, medical IoT, industrial IoT, connected transportation, and critical infrastructure examples. Finally, we examine real-world security incidents that illustrate the connection between cyber attacks and safety-critical consequences. So why safety-critical IoT? Let's look at the characteristic of safety-critical IoT systems. IoT technologies are increasingly used to monitor and control safety-critical systems. This means that connected devices are no longer limited to convenience applications such as smart speakers, fitness trackers, or domestic automation. IoT devices are now used in healthcare, industrial environment, transportation systems, and critical infrastructure. In healthcare, connected medical devices and patient monitoring systems collect and transmit clinical information. If that information is delayed, corrupted, or unavailable, it may affect clinical judgment. In industry, sensors and controllers support automated manufacturers and process control. If measurements are wrong or control actions are delayed, the physical process may enter an unsafe state. In transportation, connected and autonomous vehicles rely on sensors, communication, embedded controllers, and driver or operator decision. A cyber compromise may therefore affect the vehicle behavior itself. And finally, in critical infrastructure, for example, energy, water, and public services, which depend on control systems and communication network. Security incidents may disrupt essential services rather than only digital assets. And the important distinction here is that failures in this environment may result in physical rather than purely digital consequences. So what makes an IoT system safety critical? Safety critical A safety-critical IoT system is a connected system where failures can lead to unsafe physical consequences. So what makes an IoT system safety-critical? A safety-critical IoT system is a connected system where failures can lead to unsafe physical consequences. There are three important features here that we need to look at. The first is the physical interaction. Safety-critical IoT systems monitor or control physical processes. They may collect sensor data, trigger actuators, adjust control parameters, or provide information to a human operator. The second is safety consequences. A failure may affect people, equipment, infrastructure, or the environment. This makes the consequence different from a purely informational system. And the third is the connectivity. These systems often depend on wireless communication, gateway, cloud devices, and cloud services, remote monitoring, and distributed components. Connectivity increases flexibility, but it also increases complexity and exposure. Unlike conventional IoT systems, the key difference is that not simply that the devices are connected, the key difference is that failures can directly affect the physical world. Safety-critical IoT systems share several engineering characteristics that support safe and dependable operation. The first is real-time operation. Data and control actions must be delivered within defined time constraints. In some systems, late information may be almost as dangerous as wrong information. The second is dependability. These systems are expected to operate reliably and predictably throughout their operational lifetime. They should not behave unpredictably when conditions change. The third is continuous availability. Critical services must remain operational with minimal interruption. A short outage may be acceptable in some digital systems, but not in systems that support patient care, industrial processes, or infrastructure services. The fourth is trustworthy communications. Sensor readings and control messages must remain accurate and timely. If communication is delayed, corrupted, spoofed, or blocked, the system may make poor decisions. And finally, functional safety. The system must continue to operate safely when faults or failures occur. This does not mean that the system never fails. It means failures should be handled in a way that avoid unsafe behavior where possible. The loss of any of these characteristics can actually increase the likelihood of unsafe system behavior. So let's look at how failure propagates in safety-critical IoT. First, we will look at why failure propagation matters. Failure propagation describes how a fault or a security incident can spread throughout an interconnected system and ultimately affecting the physical process. Now, this matters because safety-critical IoT systems rely on multiple components working together. A sensor, a network link, a controller, actuator, gateway, cloud services, and human interface may all be part of the same operational chain. And a failure may start in one location but cause effects elsewhere. For example, a failure may start in one location but cause effects elsewhere. A faulty sensor may send incorrect data. The network may transmit that data successfully, and the controller may treat it as valid. The actuator may then perform the wrong action based on the data received. The physical process may then move into an unsafe state. That is why we should not only ask where a failure begins, we must also ask how it propagates. Interconnected components allow cascading effects. A failure in one component may trigger failures in other components. In safety-critical IoT, those cascading effects may eventually affect the physical environment. And the impact of a failure often depends more on how it propagates than on where it originated from. So let's have a look at the failure propagation in safety-critical IoT diagram. This diagram shows a simple chain where you have sensors, communication, controller, actuator, and physical process. The sensor observes the physical environment. The communication carries the data. The controller processes the information and decides what should happen. The actuator applies an action, and the physical process changes as a result. Below that main chain, we can see in the diagram where possible failure points are. There may be a sensor failure, a communication failure, a processing failure, or an actuation failure. The important point here is that these failures are not isolated. A sensor failure can propagate into communication. A communication failure can propagate into processing. A processing failure can propagate into actuation. And the actuator can then influence the physical environment and the physical process incorrectly. This gives us a useful way to reason about safety critical IoT. We can then ask, what happens if a sensor is wrong? What happens if communication is delayed? What happens if a controller processes corrupted data? What happens if an actuator performs the wrong action? In a safety critical system, the answer may be unsafe system behavior. That's what may happen. Let's then look at the sources of failure propagation. Failure may originate from different parts of a safety critical IoT. Sensor failures occur when sensor data is faulty, manipulated, unavailable, delayed, or physically inconsistent. In a medical context, this may mean incorrect vital signs. In an industrial context, it may mean incorrect pressure, temperature, or flow readings. Communication failures occur when data exchange is delayed, disrupted, corrupted, or blocked. This is especially relevant for wireless and distributed IoT systems where communication may depend on shared spectrum, gateways, network availability, and so on. And processing failures occur when software error, compromised controllers, incorrect algorithms, or faulty decision logic produces the wrong output. Actuation failures occur when control actions are incorrect, delayed, repeated, or not executed at all. This is the point where cyber and software failure can become physical actions. Understanding where the failure originates is the first step towards preventing them from becoming safety hazards. Let's now look at the operational challenges in safety-critical IoT. Safety-critical IoT systems must maintain safe and reliable operation despite changing conditions and operational demand. And that's why operational challenges are quite important to understand. Operating these systems introduces several practical challenges. The first challenge is the real-time constraints. Decisions must be made within strict time limits. If sensor data arrives too late, or if a control command is delayed, the system may no longer have an accurate view of the physical process. The second challenge is continuous operation. Critical services cannot tolerate prolonged interruption. A system may need to keep operating even during degraded conditions, maintenance windows, partial failure, or even cyber incidents. And the third challenge is system complexity. Safety-critical IoT systems are made of many interconnected parts: sensors, gateways, cloud services, embedded controllers, communication protocols, dashboard, and human operator may all be involved. Complexity increases dependencies and make failure behavior harder to predict. And the fourth challenge, and the final one, is dynamic environment. Operating conditions change over time. Devices move, networks change, workloads vary, and physical processes evolve. A safe configuration at one moment may not be sufficient under different conditions. And these operational challenges can increase the likelihood of unsafe system behavior. Human factors and situational awareness. So human operators remain essential for supervising, monitoring, and responding to abnormal conditions in many safety-critical IoT systems. Even when systems are highly automated, humans often remain responsible for supervision, for the escalation, override, and emergency response. And this means that safety depends on accurate situation awareness. Monitoring is one part of this. Operators need timely and accurate information. If a dashboard is showing false information, false normality, missing data, or misleading alerts, the operator may make the wrong decisions. The human intervention is also another part. Operator may need to stop a process, override or an automated action, isolate the device, or switch to manual operation. And these actions depend on the operator understanding what is happening. And finally, trust is also critical. Operators need to know when information can be trusted and when it may be unreliable. Incorrect information can reduce confidence, create confusion, or lead to poor decision. Poor situational awareness can increase the likelihood of unsafe system behavior, and the operators will possibly make mistakes, or wrong decisions at least, based on what they have in front of them. Balancing safety, security, and performance. Safety-critical IoT systems must balance multiple operational requirements while maintaining safe and dependable operation. Safety is concerned with protecting people, equipment, and the environment. Security is concerned with preventing unauthorized access, misuse, tampering, disruption, and compromise of the environment. Performance is concerned with meeting real-time and operational requirements. These objectives can support each other, but they can also create some kind of trade-off. For example, stronger security control may add latency or operational complexity. Removing a vulnerable component may improve security but reduce availability. Increasing automation may improve performance but reduce human visibility. A failed secure action may protect against an attacker but create a safety concern if it stops a critical function abruptly. And the important thing to understand here or to consider is that changes must be assessed across all three objectives together. A change that improves one objective should not introduce unacceptable risk to another. We're going to look now at some examples of safety-critical domains. So safety-critical IoT in practice or safety-critical IoT systems are deployed across many sectors where failure may affect people, infrastructure, or the environment. The engineering principles discussed so far appear across several real-world domains. We talked about medical IoT, we talked about industrial IoT systems, and connected transportation and critical infrastructure. Now, although these domains differ, they share the same challenge, maintaining safe operation despite failure and cyber attacks. Let's have a look at medical IoT systems. Medical IoT systems connect medical devices, sensors, and healthcare services to support patient monitoring, diagnosis, and treatment. The diagram shows a typical flow from a medical device to a gateway, then to a cloud or clinical analysis platform, and finally to a clinician. At each stage, there's a possible failure point. Patient data may be affected by sensor failure. Data collection may be affected by communication failure. Clinical analysis may be affected by data corruption, and clinical decision may be affected by the incorrect or missing information. All of those, the important point is that the failure may propagate through the system, and the problem at the sensor or gateway level may not remain a technical issue. It may influence the clinical analysis and eventually clinical decision making. And in this context, patient safety depends on more than the device functionality. It also depends on the trustworthy communication, correct aggregation, reliable analysis, and clear presentation to clinicians. And failures can propagate through the system and may affect patient safety. Another example is the industrial IoT system. Industrial IoT systems connect sensors, controllers, and supervisory systems to monitor and control industrial processes. This diagram shows a field sensor, a PLC, a SCADA or HMI system, and an operator. And this represents a typical control environment where field data is processed by a controller, displayed or supervised through an interface and used to support control decisions. Failure can appear at several points. Again, a sensor failure, a field sensor in this case, may fail or be manipulated. Control logic may behave incorrectly. Communication with supervisory system may be disrupted. An operator may make an incorrect control decision because the information presented is incorrect or misleading. And these failures can propagate into an unsafe process state. For example, if a sensor gives incorrect reading, the PLC may apply incorrect logic. The supervisor interface shows misleading information. The operator will intervene or may not intervene in time. The safety issue is not just that the data is wrong here. Safety issue is that the industrial process may be controlled on the basis of wrong or delayed information, and again, failure can propagate through the system and affect the industrial safety. Another example is connected transportation system. Connected transportation system integrates sensors, communication networks, vehicle control systems to support safe transportation. The diagram here shows vehicle sensor, an electronic control unit, a vehicle network, and a driver. Information flows from sensors into control logic, across the vehicle network, and into human or automated decisions. There are several possible failure points again. A vehicle sensor may fail. The electronic control unit may process data incorrectly. Communication on the vehicle network may be disrupted or manipulated. The driver may receive misleading information or make incorrect decisions. And the consequence may be unsafe vehicle behavior, which could include incorrect warning, unexpected control actions, loss of visibility, or delayed response. And this example shows why connected transportation is a safety-critical IoT domain. The system is not only transferring data, it's supporting movement, control, and decision-making in a physical environment. And again, failure can propagate through the system and can affect transportation safety. And finally, critical infrastructure as an example. Critical infrastructure systems use sensors, controllers, communication networks to deliver essential services such as energy and water. And the diagram shows field devices, a controller, a control center, and an operator. These components support the monitoring and control of services that society depends on. A device failure may affect system data. A controller failure may affect control logic. And the communication failure may affect monitoring at the control center. An operational decision may be based on incomplete or incorrect information. And the final consequences may be an essential service impact. In critical infrastructure, in this case, service disruption can affect many people at once. It may also interact with other services. For example, power disruption can affect hospitals, transportation, communication, water system. And that is why critical infrastructure security must be understood in safety and resilience terms, not only in confidentiality terms. Failure can propagate through the system and affect essential service and disrupt other services connected to it as well. Let's have a look at some examples of real-world security incidents. So you move from theory to practice. The challenges faced by safety-critical IoT systems are not only theoretical. Real-world cyber incidents have shown that attacks can disrupt physical systems, industrial operation, vehicles, medical devices, and essential services. The examples in this section illustrate how cyber attacks have affected different safety-critical domains. And in each example, we're going to focus on the same pattern. An initial compromise or weakness, propagation through a connected system, and a physical or operational consequence. Real-world incidents reinforce the importance of redesigning secure and dependable safety-critical systems. The first example that we're going to look at is Stuxnet in 2010. Stuxnet was a sophisticated malware campaign that targeted industrial control system by modifying PLC logic while concealing its actions from operators. And the diagram shows here the propagation path from an engineering workstation to a PLC, then an industrial process, and finally to the operator view of the system. The key idea is that the attack did not simply steal data. It modified control logic. That control logic influenced the industrial process. At the same time, the activity was hidden from operator, delaying detection. And this matters a lot because it demonstrates that a direct cyber-physical attack pattern, a cyber compromise, affected industrial control behavior and produced physical consequences. Stuxnet, for safety-critical IoT, Stuxnet demonstrated that controllers in engineering workstation are safety-relevant assets. If they are compromised, the attacker may influence the physical process itself. And it also demonstrated that cyber attacks can manipulate industrial processes and lead to physical damage. Another example is the Jeep Cherokee remote hack in 2015. In 2015, security researchers remotely compromised a Jeep Cherokee through its infotainment system, demonstrating the safety risk of connected vehicles. And the diagram here shows infotainment system, the path from the infotainment system to the vehicle network, then the electronic control unit, and finally to the vehicle behavior. The important point is that the initial access point was not an obvious safety critical component. An infotainment system may appear separate from the steering, braking, or powertrain control. However, because the vehicle is a connected system, compromise can propagate across internal networks and components and reach components that influence vehicle behavior. And this demonstrates that risk of weak segmentation and excessive trust inside connected systems. A system that provides connectivity, entertainment, or remote services may become an entry point into safety-relevant functions. For connected transportation, this means that security boundaries must be designed carefully. Convenience systems and safety-relevant systems, for example, should not be treated as equally trusted simply because they exist inside the same vehicle. And the compromised vehicle system can influence control functions and affect transportation safety, of course. Another example is the cyber attacks on the Ukrainian power grid in 2022. During the Russian-Ukraine conflict, cyber attacks targeted Ukraine power grid, demonstrating the vulnerability of critical infrastructure. And the diagram here shows the path from a threat actor to grid control system, then to the power grid, and finally to the public and essential services. And again, the attack highlighted the dependence of critical infrastructure on secure industrial control systems. What we need to consider here is that a cyber attack on a control system may become a disruption of a physical infrastructure service. The target is not only data or business system. The target may be power distribution, operational control, and public service continuity. This type of incident also shows the societal dimension of safety-critical systems. When essential services are disrupted, the consequences can extend beyond the organization operating the system. They may affect households, hospitals, emergency services, communications, and transport. For safety-critical IoT and operational technology, this reinforces the importance of resilience, monitoring, segmentation, incident response, and recovery planning. Cyber attacks on critical infrastructure can disrupt essential services and affect lives. And the final real environment is the medical device security advisory. Regulatory agencies have issued security advisories for connected medical devices, highlighting that cyber vulnerabilities may affect patient safety if left unaddressed. This diagram shows a medical device communicating through a network into a clinical system with consequence from patient care. We've seen this before, where the possible failure paths begin with a device vulnerability and may affect clinical analysis or incorrect analysis, which contribute to delayed or inappropriate treatment. In medical IoT, safety depends on secure design, reliable updates, vulnerability management, clinical validation, and clear guidance for healthcare providers. Cyber vulnerabilities in medical devices may affect patient safety. So, in summary, this lecture examined IoT in safety-critical context. We looked at the safety-critical IoT systems, how they interact with physical processes, and we talked about failures which affect people, infrastructure, equipment, or the environment. The second point is the failure propagation, where false and cyber attacks may begin in sensors, communication links, controllers, software, or actuators, but their effect can propagate across the interconnected component and produce physical consequences. And then we discussed operational challenges. Safety depends on dependable communication, timely operation, and resilient system behavior, and accurate situational awareness. The domain relevance in the examples we've shown, medical, industrial, transportation, and critical infrastructure systems differ in their detail, but they share common security and safety challenges. And finally, we look at some real-world incidents that confirm the risk. Stuxnet, vehicle compromise, attacks on power infrastructure, and medical device advisories all show that cyber attacks can affect safety-critical operations. To summarize, in safety-critical IoT systems, cyber attacks may extend beyond the digital domain and produce physical and societal consequences. This lecture draws on several different guidance and standards. These references are useful because they show how safety-critical cybersecurity is treated across different domains. Thank you very much.